Hi, everyone. Let's wrap up Unit 2. We just have a few loose ends to tie up. We're going to cover the rest of our key concepts of Unit 2, Part 3. Beginning looks like this. So go ahead and scroll down to the Wittig, it looks like it's Wittig, but my instructor told me it's pronounced Wittig with a V. It's not like we have to memorize these named reactions or the names themselves, but rather what are the reagents and what do they do? So here we go. So as you know, we're working on aldehyde and ketone reactions. So where's the pen? There it is. We'll start with acetone. And in the Wittig reaction, you're going to add a special reagent. I guess you call it the Wittig reagent. The Wittig reagent. It's called the phosphorus Yllid or Illid. Do I have that on here? Yeah, right here. Again, there's all these names. Scientists love putting new words on every new idea. But anyways, what you'll see is a simple abbreviation. There it is. pH stands for a phenyl ring, a benzene ring, and there's 3 of them attached to phosphorus. And then there'll be in one resonance structure, and this is the most common one, there'll be a double bond between the P, the phosphorus, and a carbon of the rest of the molecule. And then this is where you have a choice of what you want to do here. It doesn't have to be just a simple CH2 group. It could be anything. So let's put 1, 2, 3 carbons here at the end of this double bond. Okay, and with the Wittig reagent, all you do is wherever there's double bonds, you take away the O and the P and the pH3, and you connect this carbon with the double bond to this carbon with the double bond. So what you might want to do is just, excuse me, is rotate one of these groups so that the double bonds are like parallel to each other or pointing at each other. And so I got 3 carbons here from acetone, 3 carbons here. And then if I draw the O, that is acetone. Okay, then on the other side, the Wittig reagent, I have a double bond. Well, that's the end of this double bond. And it ends, the double bond ends with a carbon, and then we zigzag that way. And that's the product. So it's actually quite powerful. It takes a ketone or an aldehyde, and it makes an alkene out of it. Cool. Now, sometimes that's all you need to do on the exam. It's like, hey, if it's fill in the reagent, and I give you an aldehyde or a ketone, and on the product side, there's an alkene, one way of doing it is through a Wittig reaction. There'll be other times, though, like maybe during synthesis, where you may want to use the Wittig reaction, but your product then contains these 3 carbons that come from the reagent. So then you need to make the reagent. Okay, it's not too bad. You get to start with triphenylphosphine. Let's scroll over and give myself some more room. There we go. Let's put a little line here, separate things. Okay, so if you need to start from scratch, you get to begin with triphenylphosphine, which is abbreviated PH3P. But you know what? We at least should see what the molecule looks like at least one time. So there's 3 phenyl rings, 3 benzene rings attached to phosphorus. There we go. Phosphorus, I didn't bring the periodic table, shame on me. Phosphorus is right below nitrogen on the periodic table. And if you remember HONC, H-O-N-C, 1, 2, 3, 4, nitrogen prefers 3 bonds. Well, so does phosphorus. So phosphorus has its 3 bonds. And then for a Lewis dot structure, you need a lone pair, just like, you know, nitrogen when it forms ammonia. 3 bonds, lone pair. What an ugly looking nitrogen. That's a little better. Okay, like nitrogen with a lone pair, phosphorus is a good nucleophile. So in step 1 of making the Wittig reagent, you actually just do an SN2 reaction. So how do you do an SN2 reaction? You need a primary or a secondary halide, or maybe a methyl group on a halide. So let's see, if we want to prepare this Wittig reagent, we need 3 carbons. 1, 2, 3. And the point at which we want the phosphorus linked to the carbons, that's where your halide needs to go. And choose your favorite halide. So just remember, it has to be a primary. And then it is true that some secondary halides will work. And all you're doing is an SN2 reaction. And then this molecule, well, let's show the mechanism, right? 2 quick arrows for SN2. The phosphorus connects to this carbon through a single bond. And if you want to draw your benzene rings, you can, but I'm not going to. There's 3 benzene rings on phosphorus, and then you connect it to these 3 carbons. 1, 2, 3. Cool. Now we need a double bond. Okay. To get the double bond in place, you need to remove a hydrogen from this carbon to make room for it, right? Right now there's 2 H's. There are 2 hydrogens there. You need to remove one of them so that this carbon can make another bond, a new bond to the phosphorus. And so all we're going to use is, we need to pull this hydrogen off a carbon. And it's going to take a powerful base. And one of the most powerful, well, I think we mentioned before, is a Grignard. That's where magnesium is attached to carbon. But lithium attached to carbon is a little bit more powerful of a base. And a very common one that you can purchase is N-butyl lithium. So 4 carbons, and at the end of the chain, you can attach a lithium atom. So that's what we're going to do. And sometimes it's just abbreviated N-butyl Li. I'll be drawing mine probably. So if I'm showing reagents, I think I'll just sketch it out. And what happens, oh, by the way, there's no mechanism on the exam. I showed the SN2 because that's one we had to memorize. It's a nice application. See, let's review. So you don't have to show the mechanism, but essentially this bond right here removes a hydrogen. Maybe I should pick the other one. Let's pick the other hydrogen, it's closer. And then these bonding electrons collapse to make the double bond. And now we have the Wittig reagent. There we go. One more little detail. Yeah, let's draw it like this. There is a resonance structure. There's a resonance structure where the pi bond is acting as a lone pair on the carbon. And now that I've identified the plus charge on phosphorus, hey, you know what? That reminded me of something. When nitrogen makes 4 bonds and loses its lone pair, or uses its lone pair to make the 4th bond, then you would get nitrogen with positive charge. This phosphorus has a positive charge. It too is making 4 bonds. Cool. Anyways, I think we're done. That's how you prepare the Wittig reagent if you need to do it. First reaction, SN2 between triphenylphosphine and your choice of primary or secondary halide. And then you add N-butyl lithium. This molecule, 4 carbons, and at the end of the chain is a lithium atom. Very powerful base. That kind of activates the Wittig reagent. And then you add your ketone or aldehyde, and they couple together. Again, no mechanism, but the thought is this. There's two thoughts on the mechanism. For those who care, it's not on the exam, so you can skip it if you like. If we take this molecule, and let's draw it this way. Let's have the carbons up here, right? Yes. Let's have, trying to think. No, the phosphorus has to be here because that's going to connect there. So the carbons have to be down here. 1, 2, 3. And then we have the 3 phenyl rings. I'll flip them to that side. Not a big deal. Okay, so here's the thought pattern. that over here. In this resonance structure, carbon has a lone pair, or this pi bond acts as a lone pair and actually attaches to this carbon. And then here's the thought. That might happen in one step, and then later, this pi bond connects to the phosphorus. Or it might be concerted and they might happen at the same time. But the thought is you get this cyclic intermediate, four-membered ring, and then it breaks down. This bond goes here, and then this one goes here. And this bond becomes the double bond, the pi bond. And then this looks really funny the way it's drawn, right? This carbon's sp3 hybridized, sorry, sp2, but the bond angle is 120. So we ought to kind of move these methyl groups up. So the bond angle is closer to 120. And then on this side of the double bond, just kind of squiggle down like that. There you go. And that's the product. Let's see what else we need to know. All the previous aldehyde and ketone reactions, except for the Wolff-Kishner, all the other reactions were reversible, and we could hydrolyze them, add hydronium ion to get them to go backwards. Okay, that's not true for the Wittig reaction. It's not reversible. To go backwards from here and adding these two together to go back to the Wittig reagent, that's huge uphill in energy. Carbon in one resonance structure has a negative charge. Doesn't know what to do with that. It's not electronegative. So that's a very unstable molecule. Stable enough to exist briefly in the lab so it can do the reaction, but not stable enough to store in the bottle. Also, this is not a severe limitation, but it is one that chemistry majors should be aware of. And gosh, everyone should be aware of this. It's difficult to put 4 groups on your alkene. Tetrasubstituted is the term for that, where you have an alkene and there's 4 bonds total on the alkene. If you substitute what used to be hydrogens for other groups, other Cs, that's called a tetrasubstituted alkene. And it turns out it's very difficult to make them by a Wittig reaction because all the because of the 3 phenyl rings, it makes the Wittig reagent really bulky. And it's difficult to make. So last thing about the Wittig, if you were to try and take this molecule and react it with this Wittig reagent, this carbon connects to this carbon, right? So we would have, from the ketone, we have these 3 carbons, and then the double bond would connect to this carbon with, well, I guess there's a total 3 carbons there too. And this would give us a tetrasubstituted alkene. Turns out you get really low yields. Maybe none. So if you really want this molecule from a ketone, a better way of doing it, and it's not the only way, but a better way, is to start with this Grignard. That'd be step 1, right? Every Grignard reaction has hydronium ion as a second step. So these electrons will bump up the pi bond. They'll go up here. And then in step 2, the oxygen with the negative charge will grab an H+ and form an alcohol. So let's see, let's draw the acetone. Right here would be the alcohol. And then these 3 carbons would connect like that. And now you got a couple options. One, you could use One option is use phosphorus oxychloride, POCl3 and pyridine to remove this alcohol group. And right here's where the double bond begins. And Zaitsev's rule said the most substituted alkene would be the major product. So then you can make the molecule after. This is also a tertiary alcohol. So it might just be easier to add strong acid, warm it up, and just dehydrate it. And in fact, some of you might be saying, wait, you're using the same reagent twice? Yeah, so actually, you could say, well, start with acetone, add the Grignard, second step, acid, and then if you told me this is the product, I would hesitate and say, wait, where's my alcohol? Oh, you dehydrated. I would give you full credit. So that's kind of cool. We're actually done with all the reactions of aldehydes and ketones. Yeah, take a look at the previous video. That was loaded with a bunch of them. How many? 6 other reactions. This is the 7th one. Okay, what we're going to do for the rest of this video is just talk about some other details. We'll just call it details. They're reusing the reactions we've seen already in new applications. So it is new material, but we're not seeing any new reagents or reactions. We're just applying them in different ways. So to get us ready for the first theme, let's review something from last semester, something that was titled direct versus conjugate addition. Let's just start there, and then we'll talk about this piece later. Let's just review conjugate versus direct addition. So this is what we saw last semester. We talked about HBr or HCl or Cl2 or Br2 adding the conjugated dienes. So take a diene, right? 2 enes, and they have to alternate, double, single, double. That makes them conjugated. And you could have other groups on here. The chain could be longer, but the pattern must be that wherever in the molecule you have 2 double bonds, 2 alkenes, they're separated by 1 and only 1 single bond. That'll make them conjugated. And then where are my notes? I think I added HBr just to be consistent. Stick to that. Yeah, so I looked it up from last semester and we use HBr then. So hopefully this will look familiar. So in the mechanism, right, of HBr adding to a single alkene, we said the pi bond grabbed an H+, and you get to choose either one, the left alkene or the right. Both work. I'm just going to choose the one on the left. That's my right. I'm going to choose the one on the right. So the pi bond on the left didn't move, but this one did. And then hydrogen can only make 1 bond. So as these electrons form a single bond to hydrogen, we have to decide which carbon of the alkene does the hydrogen go to. And Markovnikov rule tells us that. The rich gets richer. So this top carbon has 2 H's. This lower one only has 1. So the hydrogen, the incoming hydrogen, goes to this carbon. So I'm going to draw it in there. And then this carbon had 4 bonds. There's an unwritten hydrogen. Afterwards, sorry, you only have 3 bonds. That makes this a carbocation. And then if we only had a single alkene, well then, opposites would then attract, right? The lone pair on the negative bromide would attack the carbocation, its positive charge, and we connect together. And we would get this product if we use 1 equivalent. That was another detail we talked about last semester. But if you start with a conjugated diene, there's a second product that results because of resonance, right? This carbocation's next door to a pi bond. That has a name. That's called allylic. That's an allylic carbocation. And it's named because it's got special, it's resonance stabilized. Even though it's secondary, it's actually much more stable than a normal secondary carbocation. That's because the pi bond can roll over to the other side. It can go here, and now the plus charge can go to the end of the chain. And you might be saying, wait, the secondary carbocation rearranged to become primary? Well, it didn't rearrange. We didn't move any atoms. The pi electron just slid over. And this is a mixture of the two. The real molecule just has 2 electrons across 3 carbons, and the plus charge is sometimes on the ends of that 3-atom system. I had an instructor tell me that resonance is sort of like Well, if we say that this resonance structure is blue and this resonance structure is yellow, the molecule is green. And if you look in real life and look at something green, it doesn't flash yellow 1 second, then suddenly it's blue the next, and then red, yellow, blue, yellow, blue, yellow, blue, there, yellow. No. So when we think, when the chemist says, oh yeah, plus charge here, no, plus charge there, plus charge there, plus charge there, it doesn't flash back and forth. It's just always green. It's always 2 electrons spread out across all 3 atoms. And overall, there's a net positive charge somewhere smeared over. And that smearing over, the technical term is delocalized, and smearing it over or spreading it out makes it more stable. Anyways, allylic carbocation re-explored there. Sometimes this resonance structure, though, can draw in the negative bromide ion, and that generates our second product. It can see this negatively charged bromine can detect a positive charge at this end, and now the double bond is in the middle of the chain of 4 carbons. And that's a pattern that doesn't just happen with, what is this, 1,3-butadiene? It happens with any conjugated diene when you add 1 equivalent of HBr. So if this is a long chain of 10 carbons and somewhere in the middle there's a conjugated diene, and you react with 1 equivalent HBr, well, sometimes it looks like 1 double bond reacted all by itself. And other times it looks like 1 double bond disappeared and the second double bond moved, right? There's 2 double bonds, 1 here and there, and then afterwards, one of the products put the double bond where it wasn't there originally. Names for this. This one is called direct addition because it acts as though it's not conjugated. It's kind of like, hey, here's my alkene, and just ignore the fact there's another one, and just remember the old chemistry of alkenes. Hydrogen goes to the end of the chain with more H's, bromine goes the other one, and just directly attacks, we're done. But the other one, the weird one, is we get resonance structures to get the double bond to move. There's some conjugation involved. Yeah, both double bonds are involved in this. So this is called conjugate addition. That generates a second product. So chemists will say, hey, what's the direct addition product or the direct product? And what's the conjugate addition product or what's the conjugate product? And other times they'll say, well, if we had numbered the chain 1, 2, 3, 4, then the new atoms, H and Br, they went to carbons 1 and 2. So sometimes we say this is the 1, 2 product. And then for conjugate addition, the hydrogen went to what used to be carbon 1, and the bromine went to what used to be carbon 4. So sometimes we call this the 1,4 product. Okay, so that was a review. Those are terms and mechanisms we need to remember because we're going to use it now in a new system that the general term is alpha beta unsaturated aldehydes and ketones. Okay, so let's start with breaking this down, figuring out what are we talking about. So let's look at an aldehyde, or let's look at a ketone. Start with the aldehyde. And then on the alpha and beta carbons, there's a degree of unsaturation. Now, when we looked at spectroscopy and we calculated degrees of unsaturation, for every degree, that told us there was at least a ring or a pi bond available to the molecule. And so what we're going to do now is just borrow those ideas. If you have a degree of unsaturation here with alpha and beta, it's implying a pi bond. Pi bond. Across the alpha and beta carbons. So remember the Greek lettering system? That was a couple videos ago. What you do is you say, okay, the very next carbon to your most important functional group is the alpha carbon. And then after that, you just keep using the Greek lettering system, alpha, beta, gamma, delta, so forth, whatever. Oh, wait, but we found our alpha and beta carbons. That's where you insert a pi bond. So what I drew here, if I just go straight skeletal, is an alpha beta unsaturated aldehyde. You can do the same thing with the ketone. Those are the alpha carbons. So then you want to make the beta carbon on the left side or the right side. Your choice. I'm going to put it on the left side. That's my right. Sorry. I'll put the degree of unsaturation over here. So here's another alpha beta unsaturated. Well, that's a ketone now. Alpha beta unsaturated ketone. And look at your pi bonds. They're following the same pattern as the diene did. It's double, single, double. Yeah, we got a double, single, double. And this one up here is double, single, double. And it doesn't matter that they're not both dienes. What's important is that they're conjugated. The pi bonds are conjugated, alternating double with single. So we don't normally do this. You can talk about unstable resonance structures. This is very stable. Everything's neutral. But you can talk about, hey, what if oxygen just gets carried away with its electronegativity? And suddenly it yanks this pi electron, those pi electrons up onto oxygen. So oxygen initially starts with 2 lone pairs, 2 bonds, but afterwards it acquires a 3rd lone pair. When it pulls this pi bond up onto oxygen, it then becomes negatively charged, and then this carbon will now be positive. And this sort of looks like atoms 1 and 2. But this part is allylic. So you can actually roll this pi bond over and draw another resonance structure where the pi bond moves over here. The oxygen, nothing changed. There's still 3 lone pairs negative charge, but now your carbocation is over here. And if this is our atom 1, this would be 2, this is 3. Now this is like a 1,4 system. Just like this. And where the double bond appears now, it's in between where the 2 double bonds used to be. Okay, I hope that's not too confusing. I don't like these types of resonance structures because I know it's kind of helpful here to connect 1, 2, and 1, 4, but this is not really what's happening in these molecules. The molecule exists mainly like this, where it's all neutral. And in here, it's like, wait, you have a zwitterion. You have something with a negative and a positive charge. This is negative and a positive. That's not stable. That's probably not happening. Okay. On with the show. So we got 1, 2. Let's take a final look at that, where the double bond ignores the fact that it's conjugated and the reagents just attack it. Everything's all normal. And the other double bond just comes along for the ride, just a spectator in a sense. And there's a second case where you used to have 2 double bonds, then you have a new one in the middle where the 2 used to be. And then the reagents add to either side of it. That's 1,4 addition or conjugate addition. We're going to use that pattern with our alpha beta unsaturated carbonyls. Okay, so it turns out, go back and look at those 7 reactions in this video. Well, 7th video of the Wittig was here, but look at the other 6 in the previous reactions, and even going back farther. If we have alpha beta unsaturated aldehydes or ketones, so what do we have? We had this one here. We had this one here. And let's throw another one in there. Let's put a couple methyls here. These are all examples of alpha beta unsaturated carbonyls, alpha beta unsaturated aldehydes, one aldehyde, and alpha beta unsaturated ketones. And it turns out that if you use sodium borohydride, lithium aluminum hydride, or a Grignard reagent, you always get a 1,2 product. That's a nice one. That's where you can just ignore the fact that there's another double bond there. You just ignore it. So let's show examples. We're going to use sodium borohydride. We're going to use lithium aluminum hydride. We're going to use a Grignard. I don't know, how about the methyl Grignard? And for all three of these, they have the same pattern that you always add hydronium ion, because these are strong bases, especially the Grignard. And so you neutralize these strong bases at the end of their reactions using some dilute acid, hydronium ion. Okay, so what happens here? Well, sodium borohydride just attacks this molecule as if it was just a normal aldehyde, right? So hydride comes off, if you want to show the mechanism, and just bumps up the pi bond. Oxygen becomes negative, no more double bond, NH plus goes in place, and you get this alcohol. And if it happened to be a conjugated alpha beta unsaturated aldehyde, no big deal. Just draw that double bond in there, it doesn't react. Same thing for lithium hydride. So the double bond, the alkene doesn't react, but the ketone does. It's reduced to an alcohol. The Grignard bumps up the pi bond right here. So if we draw the bond between the carbon and the magnesium, we can show the mechanism. It attacks this carbon and bumps up the pi bond. So everything else in the molecule, the alkene, the methyl, nothing changed there. But where we used to have a double bond O, now we have a single bond. We added this methyl. So I might draw CH3 just to highlight. This methyl is different from those two because this methyl came from the Grignard. And then hydronium ion puts a hydrogen here. And all three of these examples of direct addition just directly attack the carbonyl, directly attack the aldehyde or ketone, ignore the double bond. Everything's good, normal. It's what we'd expect. And then chemistry happens. You can also get conjugate addition. Let's put that there. Let's put my face there. Get out of the way. Okay, there's four of those reactions that we've learned in this unit that we need to pay attention to if you have conjugated aldehydes or ketones. Alpha beta, unsaturated aldehydes or ketones. So what were our three? We had this one, and it can be any, right? We'll have this one. We had this one. And I got 4, right? So 1, 2, 3, and 4. And well, let me just do this one. Okay. 4 types of reactions that are going to do conjugate addition. 2 of them are very similar. If you react a primary amine, that's primary, or ammonia, what normally would we expect if an aldehyde or ketone reacted with a primary amine? We're expecting an imine. So you don't get that if it's conjugated. We're not going to get the imine. Well, what was the imine? Just to remind ourselves. Well, that's where the O and the N trade places. The double bond O becomes a double bond at N. So where there was a double bond O, now it's a nitrogen. Hey, nitrogen, you keep your carbons. Oh, well, nitrogen started with a methyl group. Yeah, you hang on to that. And then that would be the expected product. And sadly, we don't get that. Instead, we get the 1,4 addition product, the conjugate addition product. And so what the pattern is where you had the pi bonds, in between there's a single bond between the 2 pi bonds, you get the pi bond there. That's not true. I'm showing the mechanism, which somewhere on the left side of the screen you don't have to do. So we'll just go right to the product. Atom 1, 2, 3, and 4. 1, 2, 3, 4. On carbon 4, the far end of the alkene, that's where you attach the nitrogen. So 1, 2, 3, 4. There used to be a double bond here. It's gone now. And right here is where we link the nitrogen. And nitrogen, you keep your carbons. Okay, cool. Hey, nitrogen, how you doing with the number of bonds there? Not good. It's got one carbon here, another carbon there. So it also has to keep a hydrogen. That's the product. For those of you who want a mechanism, I'll show it to you in a second. I know sometimes the mechanism is helpful for predicting products, but it's not going to be on the exam. We've got plenty of other mechanisms to worry about. Let's try it with a secondary amine now. So let's put 2 methyl groups on that nitrogen. 3 bonds of nitrogen, so I'll tuck a little hydrogen underneath the nitrogen for its 3rd bond. Well, what's expected here? Well, what we expect is where there used to be a double bond O, we're expecting a double bonded N. So I would like to make a double bond N. But then this N comes in with 2 sets of carbons, and it can't keep 4 bonds of nitrogen. So what it does is it makes a single bond here, and what used to be a double bond moves to one side or the other. Well, it can't go on the right side because of the double bond that's already there. It'd have to go over here. Okay, that's the expected product, but no, you don't get that one. Instead, 1, 2, 3, 4. The far side of the alkene, right, that's a single double bond. Right here, that's where the nitrogen attaches. The double bonded O, double bond, stays in place. This alkene pi bond disappears, and then to this atom, the alkene carbon farthest from the carbonyl, that's where you connect the nitrogen. Hey, nitrogen, keep your carbons. Oh, okay, so it's got 2 methyls and 3 bonds of nitrogen. We're done. Water under either acidic or basic conditions. So if we add hydronium ion, or if we add water under basic conditions, sodium hydroxide and water, well, what are we expecting? We're expecting hydration. So where there was a double bond O, we expected the split to form 2 single bond O's. And if you're adding water, acidic water, or basic water, these are alcohols. You form the hydrated ketone, hydrated aldehyde, you form a diol. And the answer is not today, because it's conjugated. Instead, it's 1, 2, 3, 4. The far side of the double bond right here is where you add 1 alcohol. So draw the rest of the molecule. So copy your aldehyde or ketone. The alpha beta unsaturation is gone. And wherever that ketone, wherever the alkene carbon was farthest from the ketone, that's where you connect, I'll connect it here. That's where you connect the alcohol. Yep, last one, the Gilman reaction. So that's actually new. We saw the Gilman react with acid chlorides and primary or methyl halides in a previous unit. Well, it shows up here in conjugate addition. So let's use a methyl. And we always have 2 of them attached to Culi, C-U-L-I. Let's draw that a little more neatly so you can read it. Copper and lithium, 2 alkyl groups. One of these alkyl groups is going to add to carbon 4. The alkene carbon farthest from the oxygen, that's conjugate addition. So draw the molecule, keep the double bond O, and then right here, this carbon is this one. That's where you add a methyl group from the Gilman reagent. Let me see if I'm missing anything. Oh, normally in your Gilman reaction, review. Let's see, what did we do before? We said, hey, what if you start with any form of a halide, add lithium to it, then you add copper iodide, and that makes the Culi reagent, 2 of these, add the Culi, that's a Gilman reagent. And then you have to add a methyl halide or a primary halide, And then wherever the carbon's attached to the copper, that's where this carbon becomes attached to. So you add this reagent. Let's scroll up a little bit. This reaction could be drawn where you just switch these two groups. Organic chemists, they put the molecule with the carbon on the left side. Well, both the reagent and the molecule on the left side have carbon. So you get to pick which one you want to put on the left-hand side. So I might choose to put the Gilman reagent, like I did here, over the arrow. And the whole point of this review is to kind of highlight, oh yeah, that's how you make the Gilman reagent if you need to do it again. But also, I want to just kind of compare and contrast. So when you did the Gilman reaction before, that was it. The Gilman reagent plus your halide makes the product and you're done. For conjugate addition though, you actually get an anion forming in the product and you have to quench it with hydronium ion, just like we did with the Grignard reaction. So remember the little hydronium ion at the end, and that's what forms our final product here. Okay, there's one more topic left. You can fast forward to that now if you wish. For those who want to see the mechanism, stick around. Let's do that for, I don't know, it's all the same mechanism. Why don't we do it for this alcohol one right here? Just because it's the most complicated molecule. So we start with this, we add hydronium. You know what, why don't we start with sodium hydroxide and water? And way over here on the right, the product is not the diol where there's two alcohols up here. Instead, you keep the ketone, keep the methyls, the pi bond disappears, and we add the alcohol here. Or, a little variety, you could put it here. I wouldn't put it inside the ring, it's too crowded in there. But anyways, wherever you want to draw it. Here's the mechanism, and let's make it optional. It's not on exam, at least not my exam. Okay, so what are we going to do? Normally, let's build off what we already know. So if we take away the conjugation, then the lone pair on the good nucleophile will directly attack the aldehyde or ketone and bump up the pi bond. And the hydroxide adds in here. And then in the second step, now we bring in the water molecule, which acts like the acid. It is an acid to quench this negatively charged oxygen. And we make the diol. Cool. So what used to be a double bond O, we split it. We get two single bond O's, and oh yeah, with water, there's no carbons. Oxygen, you get to keep your carbons. Well, you don't have any. Okay, then hang on to a hydrogen. Here are a couple of alcohols. Geminal diols, I think is the term for it. So this is what I want to do first. I have a good nucleophile. I want to bump up the pi bond. For the mechanism that's on the exam, you actually have two pi bonds to consider. If you want to attack this one, that's what we did before, or nature, she's deciding to bump up this pi bond. And that's what she decided to do. On the far side of the alkene, that's a ketone. On the far side of the ketone, we're going to attach the hydroxide to this carbon with a new bond. This lone pair is going to make another bond. It would be the fifth bond. Carbon can't make 5 bonds. So that makes this pi bond roll over to here. So this double bond switches over here. Wait, that would try and give this carbon 5 bonds. So that pushes this pi bond up on the oxygen. And it turns out the end result is bump up the pi bond on the oxygen. So it's kind of like the same thing with this this middle alkene here. And so after the first step of the mechanism, we still get a negatively charged oxygen like we did down here. I'll put a lone pair there. The pi bond rolled over to here. That's kind of the conjugation part. We still have these methyls, and then I'll put it down here. The hydroxy group adds to this carbon farthest from, it's an alkene carbon, but farthest from the aldehyde or ketone. And now we have a water molecule. And it's going to act as an acid. There's two ways of doing this. The shortcut is not to do it this way, right? So, oh, I forgot my byproduct. When water loses a hydrogen, you get the hydroxide ion, thus it's a catalyst. Okay, we could have the lone pair grab an H+, then we would get this molecule, which is an alkene and an alcohol on the same carbon. And that's a new functional group that you might remember as an enol. And enols tautomerize. Okay, for some of you, you're just like, what? And others are like, I kind of remember that weird word. What are we talking about? What you can do is go back to the oxymercuration-demercuration reaction. But this is the one for alkynes, triple bonds. And it's not a second step, it's sulfuric acid. Okay, in this mechanism, we talked about enols forming, which tautomerize to the ketone or aldehyde. There's a ketone in this case. So that's a long way. If you want to put the oxygen, put the hydrogen on here, then you have to go 2 more steps to rearrange the enol to the keto group, the ketone group. Or you can do it 1 step right now. Instead of the lone pair grabbing H plus directly, the lone pair comes down to reform the double bond. That's what we're supposed to get anyways. And then that pushes this pi bond to go grab the H+. And right now this carbon has 0 hydrogens on it. Sorry. But afterwards it has 1 hydrogen. And this hydrogen comes from the water molecule. There we go. That's our mechanism. It's two steps. Here's 1 step, 2 steps. Normally, 1 step, 2 steps in the conjugate addition reaction, but that intervening pi bond is playing a role here. Cool. Okay, for those of you who wanted the mechanism, I hope that helps. You can do a similar thing with the other reactions. If you need help with that, send me an email. I'll help you map those out. But again, those mechanisms are not on the exam. Cool. What else is in here? Nothing. Last topic. Let's talk about protecting groups. So it's been a while. Unit 1, we saw some protecting groups. They're still around. Protecting groups. Well, it turns out the acetal group is an excellent protecting group. So acetals, right? So let's draw this out. An aldehyde or a ketone. Aldehyde, ketone looks like that. If you form an acetaldehyde, then where you had the double bond O, put my fingers together, double bond O, you separate them, get 2 single bond oxygens, and then you attach carbon to them because these oxygens came from an alcohol. And then if it's not a hydrogen, if there's carbons on both sides, well, then you have the acetal from a ketone. Okay, you can hydrolyze it to get it back. So you can put on the acetal with your alcohol and a little H+. You can undo the acetal to get back your aldehyde ketone. And it turns out the acetal, if you stare at it, you see there's 2 ethers. And in our earlier in this unit, we talked about ether. The ether functional group is really stable. So acetals has some of that stability. They're not as stable as ethers because a little dilute acid makes them fall apart. But if you don't have any acid around, if you just have some mild oxidizing agents or some bases or some other reagents, the acetal group survives them. It's stable enough towards them. And so what you can do is you can hide or protect the aldehydes and ketones using an acetal. So here's an example of using acetals as a protecting group. Let's suppose you're doing a synthesis problem. And it won't be phrased this way on our exams because I'm trying to take a shortcut and save ourselves some time. Let's, oh, you know what? Just like nature favors the 6-member ring. Nothing special about a 6-member ring. Let's have a pentagon. Why not? And I'm going to start with this ketone with a halide. And I want to know, is there a way to change this molecule into this one? So in multi-step synthesis, let's find a series of reactions, put one reaction after another reaction to make this new molecule. And takes a little bit of thinking. But if we start with the case where there's no ketone, it's actually pretty straightforward. The trick is to see what's been added or see what's different. Actually, let's change color. So we want to take away this group and we want to put on this group. And if I do a little dotted line here and kind of hide the hydrogen, I know that's a trick. I kind of know the answer, so I knew to play this trick. But you can play it too now that you see it. If you ever have 2 carbons and an oxygen, you might consider using an epoxide in a reaction to make that product, this primary alcohol with 2 carbons. And it turns out, yeah, it's a great way to do it is to add magnesium to make the Grignard reagent. And then in step 1 of an epoxide reaction with a Grignard, right? Every Grignard reaction uses hydronium in the second step. Just have the bond here. Well, both of these epoxide carbons are primary, so it can attack either side, we get the same answer. But the Grignard carbon can add to this one, open up the ring, and then we'll have 1, 2, 1, 2, and then an oxygen, and add the acid to put the alcohol in place. So pretty straightforward. Just 3 reagents: magnesium, epoxide, acid. Done. So try it up here. Add magnesium. Well, we'll make the Grignard. And then we go in the shelves, go to the stockroom. Hey, can I have some of that ethylene oxide, epoxide? Sure. Where is it? It's way in the back. Come back in the lab. Okay, what happened to my Grignard? This did not form. This is DNE, does not exist. Remember, Grignards are incompatible with ketones and aldehydes. Grignards attack ketones and aldehydes. So in our beaker, we had, for a split second, 2 of these molecules, let's say. One was here, and the other molecule went and grabbed a little magnesium and turned into this. And then this Grignard attacked this ketone, bumped up the pi bond. And they started reacting among themselves. And this synthesis fails. It's like, dang it, because of the incompatibility of the ketone with the Grignard reagent. So we don't have to throw out the whole scheme. Still, looks like I still want to do this Grignard reaction with an epoxide. Is there another way? Is there a loophole? Is there some way to out of this problem? And the answer is yes. Use a protecting agent, a protecting group. So we're starting with this ketone, and I wanted to make the Grignard, but I can't because the ketone will react with that Grignard. So let's hide it. Let's protect it. So let's make an acetal out of it. And it's your choice. Do you want to do the standard reaction that we talked about before? Add methanol with a little H plus. And then wherever you had, show your fingers, where you have the double bond O becomes a pair of, split them apart. Single bond O's, AOs, keep your carbons, they're methyls. Or you can get kind of clever and say, hey, add a little acid with ethylene glycol. Bring in one molecule that has two alcohols, and then do the same thing. Where we had a double bond O, split them, have two single bond O's, and they are these two oxygens. And these two oxygens are linked by two carbons. They stay linked together by two carbons. Same reaction, but if you do more chemistry or you go and Google protecting groups of acetals, this is really common to use ethylene glycol. It's found in antifreeze. Yeah, go out to your radiator in your car, siphon off a little ethylene glycol. It's mixed with water and other additives, so you want to purify it before you use it as an acetal. But it's cheap and readily available. The other thing too is it's a kind of a neat reagent. You get a new ring here. It's a little bit more stable than a normal acetal. Bottom line is either acetal works. Make the acetal and hide or protect your ketone. Now go ahead and add the Grignard. So I'm going to add magnesium here. And ethers don't react with Grignard reagents. And acetals are similar to ethers. They don't react with Grignards either. So this one does exist. Yay. And so now, in one step, we add the epoxide. In a second step, add hydronium ion. Scroll this over a little bit. And then where we add the magnesium, it adds to this carbon. We have one more carbon, then attached to the oxygen. So one carbon, second carbon. This is our three-membered ring epoxide, but it got opened up. Hydronium ion has H plus over there. And then on this side, we still have our acetal. And that wasn't the final product, right? The whole purpose was trying to make the molecule with a ketone and an alcohol. So it's time to deprotect. Let's get rid of the acetal. Let's undo it. Let's hydrolyze it. So let's add a little hydronium ion, and the acetal falls apart. Okay, you can go back over here and see where the ketone is supposed to be, and then just draw it. And then draw the rest of this. Or if you're like, wait, where's my aldehyde carbon? Yeah, where's the ketone carbon? Where's the acetal? This is the carbon that's linked to two oxygens, right? This carbon's only linked to one oxygen. This carbon, one oxygen. These none, that's only one. Yeah, this is the one and only carbon that has two bonds, two of its four bonds to oxygen. So this is the carbon that later becomes double bonded to one oxygen. Kind of bring the two single bonds together to form a double bond. So find your two O's, bring them back so they overlap to form one O. Yeah, that's a good way of thinking about it. And then if you're showing all your byproducts, you get your ethylene glycol back. That's ugly. Try that again. Cool. That's how you do it. You still get to use a Grignard reagent. Just make your acetal, do your fun chemistry, and then afterwards, deprotect it, get the product back. Also, some of you may have noticed, wait, you had hydronium twice in a row. In the lab, just wait longer or warm it up. There are ways, in case you're curious, if you use cold dilute acid, not too strong of an acid, you can preserve the acetal and get this product in case you want to do more chemistry on it. You want to keep the ketone protected, or you can warm it up, make the acid a little more concentrated, give it more time, and then the acetal will react with H+ and form the ketone. You might, on the exam, say, well, I'm just going to go from Grignard, epoxide, add H3O+, and I'll go straight to here. And Dennis, you'll have to figure it out that the acid is reacting both with the Grignard and with the acetal. And I'm cool with that. I'll figure it out. All righty. I think that's the end of Unit 2. Okay. Take a look at the sample tests, use a discussion, help each other out. And I'll see you in the next video for Unit 3.